this point, you're quite familiar with the Bohr model of the atom, probably more familiar than you want to be. But we're going to use it again today because today's project is to figure out how we can look at the periodic table and identify how an atom will form an ion. In other words, what kind of ion will it form? Will it form a negative ion, a positive ion? Will it be a +1, a +2, -1, -2? What kind of ions will these form? And by the end of this lesson, you should be able to just look at the periodic table and pick out an element and say, I know that will form a +3 ion. So that's the goal. So what I've drawn on the board here already is a portion of the periodic table. I've left out the section in the middle because we don't really have a way of predicting what kinds of ions those will form, at least not using the method that we're going to look at today. So what we're going to look at today only allows us to take the first 2 columns on the left and the last 6 columns on the right and figure out from there what kind of ions we'll get. So let's look at the Bohr models. If you were to look at hydrogen, you would see that it has a nucleus and 1 electron in its valence shell. Remember, valence shell is the outermost shell. And that's the one that's important in terms of properties, because if an atom's going to react with something, it's going to react by bumping into it. And when it bumps into something else, it can give away an electron, it can get an electron, it can share electrons. There's lots of things that it can do, but always the interaction is with the outside of the atom. So it's that valence shell on the outside that's important. So hydrogen looks like that. Now, if you go down to lithium, it's going to have that first energy level, which will be filled with 2 electrons. I'm not going to bother to write in electrons for the inner energy levels. And then it has a second energy level that has only 1 electron, same as hydrogen. And if you go down to sodium, you'll see that it has 2 energy levels that are filled. And again, I'm not going to write in the individual electrons for those, but the third energy level, which is its valence shell, has 1 electron. So is this a coincidence, you might ask? Well, no, not at all. As a matter of fact, when Dmitri Mendeleev started setting up the periodic table, he was the first one to try to organize the elements. And what he did was take little index cards, and he would write the element's name on one side, and then on the other side he would write the properties that he knew. And then he took the cards and laid them out on a table, and he tried to organize them such that in a column he would have elements that all had similar properties. Well, if the properties depend on what we've got for electrons in the outside shell, then it's going to end up like this, where we have a similar configuration in the outside shell. So he was really on the right track when he did that. Okay, beryllium, we don't have anything here. Beryllium has a filled shell, and then its valence shell with 2 electrons. And then magnesium has 2 filled shells, and then its valence shell with 2 electrons. And maybe you can see where I'm going with this, because what's going to happen as we go across the periodic table is that here there's going to be 3 electrons in the outermost shell, and here there's going to be 4, and here there's going to be 5, and 6, and 7, and 8. And maybe you can see why we have the names for these families now. So boron, the inner shell is filled, second shell has 1, 2, 3. And how about if, just for the sake of saving a little time, I don't do all of these, but I'll just do maybe this row across, and I can leave that to your imagination. You can fill that in if you want to. So carbon, first shell is filled, second shell has 1, 2, 3, 4. Nitrogen, first shell is filled, second shell has 1, 2, 3, 4, 5. Oxygen, first shell is filled, second shell has 6. 1, 2, 3, 4, 5, 6. And in case you're wondering, it doesn't really matter where you put those electrons. As long as you have the right number in the shell, it's fine. You get 7 for this column. 1, 2, 3, 4, 5, 6, 7. And then lastly, we have 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, over in this column, we have what are called the noble gases. And they are noble because they're snobbish and they don't interact with anything else. That's how they get their name, actually. But the fact that they don't interact with anything else tells us that that's a very stable arrangement. They are not interested in losing electrons. They are not interested in gaining electrons. They are not interested in sharing electrons. They're just perfectly happy right the way they are. So this filled energy level that has all 8 electrons in it is the ideal arrangement. And what that means is that all these other atoms wish they looked like a noble gas. They all want to have 8 electrons in their outermost energy level because that's what makes them stable. Now they cannot change who they are on the inside. They cannot change what element they are because that depends on the number of protons. But they can change what they look like on the outside. We could go into all kinds of analogies with people at this point, couldn't we? But the elements are most stable with 8 electrons, so even though they won't change the nucleus, they won't change their identity in terms of what element they are, they will change the number of electrons in their outer shell in order to have the configuration of a noble gas. So that's how we predict what's going to happen. So let's just back up to this one because we're close here. We have 7 electrons in the outermost energy level, and it only needs 1 to become the same as a noble gas. So these will always, in order to form an ion, they will always gain an electron, which would make it F minus or Cl minus. And if you keep going down the table, you'll have Br minus and I minus, and so forth. So in this column, they will gain an electron. Electrons have a negative charge, so they will end up as a -1 ion, and that gives them the same electron configuration as a noble gas, so that means they're very stable. So let's use that same kind of thinking and see what's going to happen to oxygen and sulfur and everything below it. Now we need to gain 2 electrons. So if they gain 2 electrons and they have the same electron configuration as the noble gas, then that would make it oxygen 2 minus, sulfur 2 minus, and so forth as you go down the periodic table. How about nitrogen and phosphorus? Now one other day I told you that nitrogen and phosphorus don't very often form ions, and that is true. On occasion they do. Once in a while they're more apt to share electrons. We're going to see these much more often sharing electrons. But if they were to form an ion, we would need 3 electrons to get the configuration of a noble gas. And so sometimes you will get this. But it takes a lot of energy for 3 electrons to be transferred, so that's a little bit less common. Carbon and silicon, they don't even form ions. It takes way too much energy to transfer 4 electrons. So these guys will share electrons, which is the subject for another day. Boron and aluminum. Now we're into having to gain 5 electrons. That's way too much energy. So what these guys will do is actually lose electrons instead. Now boron actually tends to be way more apt to share electrons, because losing electrons that are kind of close to the nucleus takes an awful lot of energy, but losing electrons that are a little further away from the nucleus isn't so bad. Like, think about how these electrons are held very tightly because of the positive charge in the nucleus and the negative charge in the electrons, and there's this attraction. So it's kind of hard to pull them off if they're close to the nucleus. But if you go out another energy level, then they're not held quite as tightly. It's a little easier to get them off. So boron will tend to not form an ion. You're not going to see boron too often. But you will see aluminum. So I'm going to draw aluminum because I didn't do that before. So here's aluminum with the first energy level, second energy level. Remember, these are filled. And now we go up to the third energy level, and it has 3 electrons. Now this one's further away from the nucleus, so they will be lost. And aluminum will tend to, here, I'll just draw X's through them. They will just tend to lose all 3 of them. So now what do they look like? Well, they look like a noble gas because we've got 2 filled energy levels. This one would have 2, this one would have 8. So if you take off those outer electrons, all of a sudden it does look like a noble gas, and it's happy. Actually, it's stable. Atoms don't really get happy, even though we talk about them that way. So aluminum will tend to form an ion with a +3 charge. Now, using that same kind of thinking, you can imagine what's going to happen over here. We're also going to lose these outermost electrons, and so we'll tend to form ions like, now I have quite frankly never seen a beryllium 2+ ion, and I think that's kind of in the same category as boron, where because the electrons are so close to the nucleus, it's too hard to get them off. So these two atoms will tend to share electrons. And let's talk about these two also and say that they will share electrons. You're not very likely to see ions with any of those. However, magnesium will definitely form a 2+ ion. Remember, losing electrons? I know this, you have to be careful not to think of losing as minusing and trying to give it a minus sign, because this negative charge, that negative sign, that's not about minus, and this positive sign is not about plus. So when we lose electrons, electrons have a negative charge. We end up with more protons than electrons. The charge is positive. So Mg2+, and if you went down the periodic table, you would see calcium 2+, and so forth. I think strontium's under that, and barium. And then over here, all of these, even though the electrons are pretty close to the nucleus, it is way more stable to have that electron missing, and so they will actually lose their electrons, and hydrogen will form a +1 ion, lithium will form a +1 ion, sodium will form a +1 ion, potassium will form a +1 ion, and you can keep going down that whole column, and they will very easily form +1 ions. So now you know. If you're asked, what kind of ion will this form? And by the way, I won't give you examples that don't form ions. You can look at the periodic table and know that everything in this column will be +1, +2, +3. We'll skip that. -3 if they form ions, -2, -1, and 0. These guys are very happy the way they are, remember. They will not form ions.